our next speaker. V Gooje is a member of Thornton Tomasetti, our host for today. We're very appreciative. Vamshi oversees and develops initiatives for building analytics for the building sustainability practice. He works with firm-wide practice areas to support building science-related projects. His expertise includes building science, energy, and daylight simulation programs in sustainability. He has more than 10 years of experience in the field of architecture and building science. He holds a bachelor's degree in architecture from India and an MS in climate responsive architecture from the Arizona State University in Tempe. And the title of his presentation is Applying Tools for Cross-Practice Collaboration. And I think just a few more.
Hello, can you hear me? You always have technological challenges. So while Chris is setting up, let me start. So my experience actually has been in energy modeling and daylighting simulations for over a decade. And I've been using complex energy simulation programs such as eQuest, Dodu simulation engines, and Energy Plus, Radiance, and other daylighting simulation tools. So I guess we can sort of retire those programs because they are legacy tools now, feel like, because now what we have with Grasshopper tools, we can do much more collaboration with the design team early on, and which is what we've been planning to do in all this while using these advanced programming. But one of the things that we face is the inertia with these programs is they take a lot of time. They take a lot of time, and it makes it really impossible to use ahead of time in the design process. So when Jonathan Schumacher actually introduced Grasshopper tools and Diva tools to us, it really got us interested because now we see opportunity for actually merging what we are doing with complex energy simulation programs and what Grasshopper tools can do in terms of design parametrics. So cross-practice collaboration, which is the topic of my presentation today, is at the core of what we are trying to do company-wide. It's not just in terms of technology itself, but in terms of how we can produce a valuable product at the end of the design process.
I'm sorry.
Oh, it's okay. I'll manage it. So that brings to the point different practice areas we have in-house. We have structures, skin, performance, property loss consulting, construction support services, and building sustainability. So I'm part of the building sustainability group. So we do whole building energy performance kind of simulation. So we're looking at the climate, we're looking at the envelope, we're looking at the internal loads, how it impacts the building energy performance, daylighting aspects, and HVAC systems, air delivery and plant side as well, and on-site renewables and life cycle costs, so on and so forth. So we are looking at this problem holistically. Well, when you look at different practice areas we have specialists, analysts doing very specific focused areas. For example, structure group is looking at the massing and how to optimize the massing and the shape and the orientation of the building, for example. And it actually creeps into the architecture side as well, but we are trying to do and enhance our services that way. And skin is looking at the facade treatment. One of the issues that we have seen is that these different practice areas are, as they're looking on focused areas, we want to enhance these services by looking what the impact would be on the overall building, not just facade. And I'm not going to touch a lot on the rest of the practice areas because we do have some synergies among these different practice areas, but they are not relevant to the topic that I'm covering today. So why we're doing what we're doing, and this is what I was trying to get at is we are not myopic, we are not short-sighted in this. We want to take a step back and figure out the vision for the project and the goals for the project, and we want to see what the project is trying to achieve. So that is where our integration and collaboration with different practice areas come here. So one of the things is when can we really make this impact on the design process? As you have seen this chart probably many times, there's less effort in the early design phases and more impact on the design. And as you keep moving toward the end of the project, your impact is going to be less, but you are putting more effort. So nowadays, what we have been doing in the past is we are somewhere there. So we're putting a lot of effort for nothing, in a way. You are mostly focusing on system side, but you're not able to optimize your design. So we want to move, that's our goal, is to move to the left side of this chart. And what we see here is a typical work plan, how we are operating the standard operating procedure in the industry right now. So the first chart, we can see like all the consultants are hired, and even this hire is happening in several tiers. Usually the environmental consultants are the second hires or second tier hires. So we kind of lose the opportunity to make any impact on the design. And I personally feel there are several reasons why this is happening. One is because it's familiar, this is the process, and this is how the industry has been doing, and this is how we want to be doing. And the second one is technological hurdles. So one of the things to overcome these shortcomings is actually education and awareness, which we are trying to do with the client more so nowadays. But if we can actually use tools that we are developing in-house to show that this can be done more effectively without increasing the project budget, then I think we have a very good case. So our ideal situation would be we get hired and then we actually move the process to the pre-design or schematic design. So again, reiterating the term of being focused on particular analysis, what we are looking here is optimization of louvers based on daylighting metric and radiation. But is this really giving us a picture of whole building performance? I personally don't see it. So you may be getting a good daylight in the space, but is it optimized for energy performance? Is it interacting with the HVAC systems? Is it interacting with artificial lights and schedules and so on and so forth? So we want to introduce that whole building performance into our practice. So maybe we want something like this. I don't have a movie, just to keep it simple. So this is combining what structures is doing, what skin is going to do, and what sustainable group is going to collaborate with all these practice areas. So here we have the inputs as aspect ratio of the floor plate, number of stories for the building, and the massing of the building. And then on the left side, we have different metrics. So eventually our goal is to have several metrics. Right now we see as embodied carbon, and we see operational cost and the mass of the building itself. But we want to introduce daylighting, water, and other kinds of metrics. So we are getting real-time feedback as we are changing the design parameters. And this is going to be really valuable in the early design stage, we feel. And then as we move on to the next stage, we can use more complex models to study the HVAC systems and plants and so on and so forth. So the first thing, because we are planning to use these tools in the commercial sector, we want to develop a level of confidence in-house so that we can tell our clients, yes, these results that we are showing you are validated. First of all, I'd like to thank Advanced Computational Modeling Group, which is an R&D department of Thornton Tomasetti, which is basically the core of this whole grasshopper tools and all kind of digital technology. And Chris Mackey actually, especially for putting together a lot of this studies together. So what we did is we first created a shoebox model in Rhino, and then we ran the simulation in Viper. This was a year ago when Ben Silverman, who is not with us, he was interning with us, at that point. And then we ran similar shoebox models in Design Builder, and we compared the results. So what we found was there were some discrepancies between the heating and cooling energy, Viva and Design Builder in heating and cooling energy loads. And as you can see on the left side, the Viper component had very basic inputs, people, internal loads, and lighting control. So we did not have enough capability to change the defaults. So then the next generation of Viper component, as you can see, we have much more capability to adjust the parameters such as the coefficient of performance of systems and schedules, internal gains, and infiltration, so on and so forth. And I think John Sargent actually helped Chris Mackey actually to help with this calibration process. And we can see within a reasonable amount of error, they are pretty close what Design Builder is producing as output and Viva is. And this gives us a level of confidence to use these tools now. And this, what we're looking at is a typical summer and winter day for both heating and cooling. And as you can see here, there are some discrepancies in the schedule. That's why it's dropping right off here, whereas Viva is slowly ramping down until 11 o'clock. So those discrepancies can be attributed to this difference in the schedules. And the next study I'm going to show is using shade array. I like the name of that. And we actually, on top of that, said shade roses. So what we did here is we created an octagonal space with windows on all surfaces, all orientations. And we try to optimize the window shade. So one thing I want to mention here is, even though some of these tools may look as if they are being used in isolation, when I'm talking about whole building integration of all the systems, but in reality what we are doing is we are anticipating to use these tools as a plugin and create a complex network, so that in the end we have the output, but we also have good knowledge of the background, what's happening. So it just helps in QC process of what's causing the outputs. So we are not just looking at the inputs and outputs and saying, well, that's good, let's go. But sometimes these results don't make sense. So then we would want to have some ability to investigate. So in shade rows, what you see here is we are using TMY2 data or TMY3 data and optimizing for Boston climate here. Does it look a little skewed here? Or is it just my eye? Okay. So what you're seeing here is when we are optimizing the shade, the blue indicates there are some energy savings, because this is Boston climate, which is cold climate. So you want more solar gains. So if you're in the gray area, you can't quite see the lines. That's the middle point between savings and the penalty. And you can see penalties on the red side. So we quantify that. And then we ran for different climates. So this could be a great climate consultant sort of tool, where you can run the same model in different climates and see what is the optimum depth of the shading device. And then another round of simulations where we used different kinds of passive strategies. For example, here I'm just showing the natural ventilation and air source heat pump and ground source heat pump. Actually, this particular diagram really got me interested, because we always preach that you have to go in sequence. You first optimize your envelope and your loads, and then once you've got really small loads, then you use your systems to deal with those loads, and then you have better performing building and with less energy, carbon footprint. But this one was quite interesting in the sense, just because we are using ground source heat pump, which comes with high coefficient of performance, we were able to see that the depth of the window shade has changed a little bit from the baseline there. And after talking through, one of the things that we found was it's because the temperature of the municipal water, if you just run through it, it's just enough for cooling. So the energy that you're using is only pump energy. If you were to increase the depth of the shade, you will be penalized in the heating cycle, and then you're using mechanical systems to heat it. So the balance is gone. So which was very interesting because I could have never thought that before. So these kind of things actually really help us address or think outside the box. The next exercise is fruit pattern. This is just to mess up your eyes. You can look for a little bit. So here Thornton Tomasetti works on a lot of stadiums, and one of the stadium that we worked on, which is confidential, so I cannot say the name of it. So it is in a cold climate, and the idea was to enclose the stadium completely on top with ETFE roof. And the concept was to use 2 layers of ETFE roofs, so the top layer and the bottom layer. And one of the ideas we came up with is have frit pattern on the top layer and frit pattern on the bottom layer, and offset with X distance, and also offset with Y distance, so they're not superimposed right on top of each other, and come up with a solution so that we can control the sun angle at the critical point in the year, so that we are getting enough light, but we are actually avoiding solar gains. So that was the concept. So we have the baseline here without any frit pattern, and then we created a test patch here where you have the top layer and the bottom layer, and right under the bottom layer we created a radiation test patch there. And then we looked at the solar vectors projected right on the test patch. And now what we did is we actually eliminated the vectors that were passing through these gaps, and only accounted for the ones that were hitting the patch. And we made a simple assumption here that when you have cooling load in the space, then when you add up the direct beam associated with the solar vectors that are imposed on the frit pattern and aggregate them, and the kilowatt hours per square meter, kilowatt hours you get out of that is the savings, or that's how much heat you're actually avoiding in the space. But if you had heating energy or heating load inside the space, then that would be the penalty of your design. So this can be applied even with the beam gains, and it's a very simplistic algorithm, but we can develop on these algorithms further. And these are different generations of frit pattern that we got, and this is the final generation of frit pattern. So one of the ideas with that, back to the frit pattern, is also we were thinking of what if we actually make the ETFE roof dynamic. So we inflate the roof so that we can even control the altitude and also azimuth at different points of time. And because of this parametric capability we have now, it's quite more possible now than before. And some of the other tools that we actually created for energy side of it. The first one is the ground temperature. So we used ASHRAE fundamentals to use some algorithms where the key assumption is that at 25 centimeter below the grade, the temperatures are weighted average of the air temperatures over the previous 10 days. So we have that diagram, which we're calling surface ground temperature. And then we have soil conditions. So soil conditions actually determine at what depth the temperatures are stabilized. So below that temperature, we are pretty much seeing the same temperature profile. That's what you see at the purple line. And of course, until you go really deep enough, then you start to tapping into the mantle temperatures. But we're not going to go that deep, theoretically speaking, at least practically speaking. So then we came up with a logarithmic function to to extrapolate or interpolate the data for any depth of this ground. So the reason we are doing this one is, like, if you want to study in early on stage whether a ground heat exchange system can work for this particular project because of its location, then we can know. And if it can work, what are the COPs that we can gather from that kind of climate and the space type. So we connected to another component that we developed in-house with ground source heat pump. And here, one of the key assumptions we made is that heat pump system actually works at 30% of Carnot efficiency. Carnot efficiency is the ideal efficiency of an engine, which you probably don't want to use it because it's probably very efficient, but it's not practical. So we also have the ability to change that 30% default to some other number if we find from peer-reviewed literature that there's another number that we should be using. But at least we have this thing set up. And then we can use the same component, and instead of using the ground source, the ground temperatures, we replace that with outside air temperatures. Then we get the air source heat pump coefficient of performance for both the heating and cooling side. So then we looked at also the economizer. I believe the thermal component doesn't have economizer capability, but in some of the cold regions, it's quite used. It's very standard. So basically what we do is we are looking at the outside air temperature and the high dry bulb limit for which, above which there will be cooling load, below which there will be heating load. So, or there's a thermal band between the heating kicks on. So we are setting that temperature, and then we are plotting what is it doing to the cooling load. So in this data visualization plot, you can see this is without the economizer cycle, and this one with the economizer, the blue. So we can quantify like how much we can save on the cooling load itself. And same thing with heat recovery. So we are using the exhaust stream and seeing how much we can recover, and you can plot the chart and see whether heat recovery is something that is conducive or not for that project. And of course, sometimes the fan energy for running the additional CFM or passing it through the enthalpy wheel is going to be higher than the heat recovered. So we want to make sure that it is feasible in that particular project. And the other interesting subject that we have explored here, this was Dan Noll's brainchild, basically the whole theory behind it, is a thermal decay. And when we are using underfloor air distribution, thermal decay is basically the temperature increase from the source to the diffuser. And because there's not enough thermal mass between the plenum, the underfloor plenum, and the space itself, there's going to be instantaneous heat exchange. So that's going to impact the cooling load. So if you were doing that with overhead systems, then you do not experience that, but with underfloor system you could. So as you can see in this data visualization chart, this brown peaks are because of underfloor distribution, even though you're supplying the air at a higher temperature. And because you do, and also we added the capability of different systems in the component. Let me actually go back a second. So here you can see the different systems that we can analyze: displacement ventilation with radiant floor, or underfloor air distribution. And we're specifically choosing these two because they are actually delivered at a higher temperature, or the delta T is small between the room temperature and the supply temperature, because it is delivered at close to the occupants. And another component we also added was on-site renewable. So we used a BREP to see how much solar we can collect on that, and we plotted on that the heating load to see if we are oversizing it or undersizing it, or what's the right size for solar thermal collector. In conclusion, where we are, or where we were a few minutes ago, I guess, is like right here. So we're doing a lot of hard work for nothing. And then we are able to actually move forward. And with the help of these tools, we are at least anticipating to be there. And also, in conclusion, we want to say that this is real-time feedback, so we can go to the meetings with all these models set up, and right in the meeting we can actually give feedback to the design team. This works, this doesn't work. And design decisions can be made on the spot, and it will set the motion in the right direction. And the other thing that we think is transparency as well, because we're not just relying on the output itself as is, but we are also investigating whether these outputs make sense or not, or it gives us additional capability to see what's going behind the screen. And the last one is integration in terms of both tools and how different practice areas are able to collaborate with the help of these tools, and at the same time educating internally, externally, and bringing up the awareness that we can actually do a better job with these tools. And I think with that, to conclude, I don't know if I finished on time or... Okay. Thank you.
Thank you very much. Are there questions? Yeah, Rahman?
At this point, are you still looking at single zone with adiabatic surfaces, one exterior, or are you looking at like a 5-zone floor or a system?
Yeah, I mean, we are. This is all developed based on single zone systems. That's a limitation. But Mustafa, I know he actually showed me something the other day. We are looking into expanding that capability to multiple zones. And that's a great question, because when you're working on big projects, your space type is not just one singular space type, but you may have mixed use. And in those cases, some technologies work in some space types and some in the other. So we want to explore that side of it. And that's the works, basically.
I really love seeing that. I mean, in a way, what you start doing is using Grasshopper as a tremendous replacement. Is that right?
Yes, pretty much. I know Streaker.
No, I think that's an interesting observation. Is the solver strong enough to do that? Feel that comfortable that this works? I see the benefit in terms of workflow.
Yeah. I mean, the way that we want to use it as an early design tool, I mean, we don't want to rely on the data to the fact that it's very accurate output, but we're going to say, okay, this is a strategy and this is a strategy. So what is the difference between those two strategies? So we're just looking at the delta between the strategies, so that we have some idea whether the strategies work or not, and also it just puts us in the right direction in the early design stages. So eventually we would translate all this database into Energy Plus or eQuest and study more in depth. That's the idea. But I wouldn't claim that it is competing with Transys really at this point, until we use more. I'm just saying it because we have transport.
It's tell me what you mean.
Right. Making outside the door.
Actually, one thing that's a study that some of you might want to look at, that want to do this, from Timur Dogan, that is published next month at Building Simulation. He basically showed you get pretty far by abstracting a whole building into a few shoebox models. And if you have a clever algorithm which is presenting or breaking it up, so that each shoebox represents a meaningful size of the building, you can in certain instances actually model a building specifically doing schematic design just with a few boxes, even if it's a full city. And that you can just use Viper directly to do something. Even though, of course, there's a lot of merit in certain cases of doing multiple zones, doesn't always that's often necessary.
Correct.
Thank you very much.